Physics 2 Lab 3 by Ellie Maley. Introduction. So these are the key concepts that will be used throughout the lab. The loop rule, which is the sum of all the electrical potential differences around a loop is zero. The node rule means the current flowing into a node must be equal to the current flowing out of it. Electrical resistance includes Ohm's law, resistance in parallel, and resistance in series. And you can see these equations here. Capacitance measures how much charge can be stored in a capacitor for each unit of potential difference. And this shows the equation that we use. This is the equation for capacitance as well. Now, to do the experiment, we had to make some assumptions. The experiment was using the principles of energy conservation to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits. And we assumed that the resistance of the wire and ammeter is negligible, as well as the EMF equals the change in capacitor plus the change in resistors. Now, the observed model is shown here. The system was a voltmeter and the surroundings were the circuit, as you can see in this image. Here's also another interpretation of that. Now, here I show a simple and open circuit. We can see that the predictions I made were I1 equals I2. So 47 plus 100 equals 147 ohms, which is what was in this simple circuit. The actual was 0.020 amperes. And then in this open circuit, the predicted was 3 volts, as you can see here, but the current was 0 since it's open, and the predicted was actual values. Potential differences are shown here, and I calculated them all and put them here. The current stays the same throughout the entire thing. Now, the ammeter in parallel. As you can see here, the circuits are in parallel and not in series. The current increases to 0.06 amperes, and the current splits into junctions. So as the refraction decreases, I increases. Now, to calculate resistance, I use these formulas here. I have R47, R1000, R wire, and R ammeter. To calculate these, I use the resistance formula. Now, charging times. Here I made an Excel graph about how it made a slope, a downward negative slope, that shows the 10 ohms resistor has a charging time of 13.6 seconds and discharging time of 13.4 seconds. The 20 ohm resistor had a charging time of 22.7 seconds, while the discharging time was 24.3 seconds. So this creates this downward slope, as you can see here. Now, errors that could have occurred in this lab were human error when I stopped the stopwatch for each current in each circuit, and also lack of precision. The ammeter is not 100% accurate. There are some errors within the ammeter precision measures. Now, here are the what ifs. What if you were doing this experiment in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it affect the circuits you hooked it up to? Well, a real ammeter actually has a non-zero resistance. The current in the circuit would have decreased, and the internal resistance of the ammeter can cause small voltage drops due to the ammeter itself. And so this drop would affect the voltage, and it would affect some of the other components in the circuit. Now, what if you're doing this experiment in real life and use a real battery to charge a real capacitor with no resistor in the current? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Well, the ideal model predicts that the capacitor would reach full charge very quickly, and there are no resistive losses, and the voltage across the capacitor would immediately rise to the battery voltage as soon as the circuit was closed. So the prediction is not what would happen in an ideal situation. Thank you.